Good afternoon, students. Welcome to today's lecture on PRPC. And we will wait for 5 minutes for your friends to join. Okay, so let's start. We were talking about catalytic reforming from chapter 4. And in catalytic reforming, we have seen the process steps, process reactions, and we have seen what is alkylation. Okay, and I showed you a video on alkylation. Now we'll move to the next process of reforming, which is catalytic isomerization. Okay, which is nothing but conversion of n paraffins into isoparaffins, and this helps in two ways. The first one, good quality gasoline due to the improvement in octane number, and second one, for alkylation purpose, isoparaffins are required because n paraffins cannot meet this demand. If you remember the alkylation reactions, we are working with isobutenes. Okay, so that's why we require isoparaffins. So we need isoparaffins, which can be achieved by catalytic isomerization. Then feedstock suitable for such operation should mainly consist of C4, C5 and C6 fractions. All type of catalysts used in catalytic cracking and reforming operations are certain to bring about this reorientation of the molecules. At present, aluminum chloride catalyst is widely used for catalytic isomerization, and noble metal catalyst is also used in the fixed beds. Then isomerization with a platinum catalyst. The catalyst used in this process is similar to platinum based catalyst used in catalytic reforming. The main difference is in the number of reactors and the reaction conditions. When you are changing the catalyst, this is the main difference. There is only one reactor. A catalyst promoter like hydrogen chloride is continuously added during the reaction to keep the activity of the catalyst. So this is the condition of the reactor in which you're using platinum catalyst. And then aluminum chloride isomerization. So you have the reactor here. Then you have catalyst recovery system in two. Then here you have the hydrogen stripper because you are using hydrogen chloride. Then here you have the HCl stripper, and then here you have the caustic neutralizer, and six is a fractionator in which you get the paraffins, isoparaffins. The process can be conducted in 5 beds where catalyst is usually deposited on various carriers. The catalyst is non-regenerated. It cannot be regenerated. Hydrogen and hydrochloride are continuously added into the reactor. Desulfurized and moisture-free feedstock with recycled N-paraffin is mixed with the hydrogen and heated, which is the feedstock is almost 6 C5 to C6 carbon molecules. This mixture with recycled hydrochloride gas enters the reactor 1 where the catalyst is spread on alumina or bauxite in a fixed bed. The effluents are passed through a catalyst catalyst recovery system and then through a pressure releaser where hydrogen separates out. Later, HCl gas is recovered in a stripper. The effluent is given a caustic wash and finally sent into a fractionator to separate I-paraffin at the top and N-paraffin at the bottom. The N-paraffin is recycled back, and we need the I-paraffin for other purposes. And this is aluminum chloride isomerization process, which you have seen here also. Okay, they have explained almost the same thing. Then comes the last one, which is the catalytic polymerization. So polymerization is a process in which the substance of low molecular weight is transformed into one of the same composition but higher molecular weight, maintaining the atomic arrangement present in the basic molecule. So you're going to have the same composition, but by increasing the number of monomers, you're going to increase the molecular weight. Composition is same. For example, if I say C6H12O6, then C6H12O6 will remain the same. But the molecular weight can be increased. How? By increasing the number of glucose units. That is how you can make it as starch or sugar. Okay, that is polymerization. It has also been described as a successive addition of one molecule to another by means of functional groups such as that present in an aliphatic olefin. By adding, if it is methyl benzene, if we have a uh, propionaldehyde, something like that. Okay, so in the petroleum industry, polymerization is the controlled process by which olefin gases are converted to liquid condensation products that may be suitable for gasoline or other liquid fuels. The feedstock usually consists of propylene, propene, and butylenes or butene. from the cracking processes. So the feedstock for polymerization, you require propylene, which helps you to form polypropylene. Then you have propenes, then you have butylenes and butenes. Then a polymer gasoline represents dimers and trimers of olefins. Polymerization is intended to convert off gases of the thermal crackers. Then thermal polymerization is not very effective, hence only catalytic polymerization is industrially opted. Olefin polymerization is brought by certain catalysts like copper pyrophosphates on charcoal. This is one of the catalysts used in olefin polymerization, and sulfuric acid, phosphoric acid at low temperatures not exceeding 200 degrees Celsius, because you need to achieve the catalytic activity. So if you go beyond 200, the catalyst will be deactivated. The reaction is exothermic, liberating almost 225 to 300 kilocalories per kilogram energy of polymer formed. So this is a polymerization reaction. Okay. So polymer gasoline, what? How do you get a polymer gasoline? So first, your feedstock, which is your olefins, they come into the caustic and water washers, which is in one. Then it goes into the dryer because it has been washed. It needs to be dried. Then it goes into the reactor, which is fed with a catalyst, and from the reactor it goes into the separator, and from the separator it goes into the fractionator. From the fractionator, the lower part is taken out as stars and the upper part is taken out for olefins, I mean your gasoline. Okay, that's what is explained here. So that's about the catalytic polymerization. I'll try to get a video for this, so please wait. First, we will see isomerization, its chemistry. Then we will see polymerization. We will see both the videos now. So first, I'll play the isomerization one. Okay, here you can see the video screen. It's about isomerization and its chemistry behind it.
Chemistry. Remember that isomerization is nothing more than trying to rearrange the structure of a compound or a molecular formula. And what we're going to keep is the total number of carbons and hydrogens, and of course if there are other atoms, we're going to keep the total number. We're going to keep the total number of single bonds, double bonds, and triple bonds if given. And what we're going to do is essentially just try to modify the structure overall. Now remember that, for instance, pentane has 5 carbons and a total of 3, 5 times 2, 10 plus 2, 12 hydrogens. As you can see here, isopentane, please count them out, 5 carbons, and if you were to count all the hydrogens, you will count 12 hydrogen. So you can see here, this is linear, this is branched. Now remember that typically branched hydrocarbons will increase the octane rating because they tend to not combust easily, and the linear ones will interact easier with oxygen. So that's a very rough estimation, but typically iso structures are much more high on octane rating than N structures. So here we go. Primary reaction is to convert normal paraffins. Remember, normal stands for linear. This is N-pentane actually. When we say pentane, actually we cannot know which one it is. We need to state either N-pentane, isopentane, or sec-pentane, and so on. To isomeric paraffins. Isomeric, as the name implies, has a iso branch. Olefins may isomerize and shift the position of the double bond, so that's interesting. So we have here 1 butane. 1 butane is something like this: 1 carbon, 2 carbons, 3 carbons, 4 carbons. 1 butane has the double bond here. what we try to do is to convert this to either this one right here or this one right here. And then, of course, we try to hydrogenate this in order to convert this to a useful material. Cycloparaffins, technically naphthens. Remember, naphthens are cycloparaffins. Easiest example is this 3-carbon molecule, 4-carbon molecule, 5-carbon, and you already know these ones. These ones are common, cyclopentane and cyclohexane. In this example, cyclobutane, this one right here, will be broken into cyclobutane, which is this one right here, which later on can be converted to these ones here, and then converted to more stables, and then convert to isobutane. So here's an example. N-pentane can be converted to 2-methylbutane. Why butane? You have the long chain, which is butane, for carbon chain. And in the second carbon, you have this other carbon, methyl branch. Or 2,2-dimethylpropane. Propane stands for the longest chain, which is 3-carbon. And in number 2, we have methyl branch, 1, second methyl branch. So that's why 2,2-dimethylpropane. Now let's get a little bit more into the catalyst side, which is what you're going to cover mostly here in the overall conversion of refinery. In the refinery, you're going to have zeolites, which is something like this, cubical structures which favor sites of reaction, and chlorinated alumina. And you can see here, the idea is to have micropores, so it's easy way going in and easy way going out. But in this specific case, you're going to have a higher interaction or more area to interact with your reaction. Remember that catalyst, what we're going to do is favor the rate of reaction. Zeolite catalyst requires higher temperatures, so that's a disadvantage, and provide lower octane boost, so that's bad. So probably you're wondering why will we want to use zeolites. We're going to see it later, essentially because these zeolites are heavier, or it's a little bit more complicated to poison it compared to chlorinated alumina. In the other hand, chlorinated alumina will have a higher octane rating, doesn't need to operate at high temperature, higher sensitivity, but because of the same higher sensitivity, we're going to require to remove or pretreat most of the feeds. So we need to remove oxygen, water, sulfur, nitrogen, and other metal-containing compounds. Zeolites, in the other hand, are crystallite silicoaluminates that are used to give an acidic function as a catalyst. Remember before we have seen a lot of hydrogen sulfide or sulfuric acid, phosphoric acid interaction, even hydrofluoric acid. Those are providing a proton, which is the acidic catalyst. Metallic particles of platinum are impregnated on the surface of zeolites. These particles act as hydrogen transfer centers. Remember these hydrogens. The zeolite catalyst can resist impurities, so that's an advantage compared to the chlorinated catalyst. Does not require extensive feed pretreatment, which is awesome, and that means that our catalyst is going to last longer. But as stated before, has lower activity, will require high temperatures, and it's one for the other. Now let's continue to the process description of isomerization.
So that was about isomerization, and they talked about the two catalysts. Okay, and they are saying zeolite is comparatively giving low octane number when compared to chlorinated aluminas. Now we will see the next one, which is polymerization. This is just on polymerization
right now, but these tiny crystals, known as pellets, are the chief component in making a wide array of plastic and is the end result of polymerization. You might be wondering, what is polymerization? Well, polymerization starts when a catalyst meets with a basic molecule to make longer, more complex particles by the breaking of double bonds. And the process of creating these repeating structural units are known as polymerization. The origins of polymers comes from reservoirs of oil and natural gas being pumped, piped, and refined into side products and byproducts. This is ultimately where feedstock comes from, which is the first step in polymerizing plastics. And the feedstock then goes into a steam cracker, where steam is used to heat furnaces to break down the feedstock into their base parts through a maze of blazing hot pipes. It is then cooled into a dense liquid-like gas where it is then separated out into ethylene, propylene, butadiene, and cracked benzene. It is then sent to their assigned tanks where it awaits to be used. Once it's determined what type of plastic or polymer is going to be made, the monomer gas is preheated and ushered into the molecular sieve, where water and other contaminants are filtered out by a material called zeolites. The dry gas is now ready to interact with the heart of the system, and that's the stirred gas reactor, where polymerization is continuously carried out, where propylene, ethylene, and hydrogen are introduced to the reactor. Solid catalyst is introduced to the reactor to kickstart the formation of polymers. While this is happening, a lot of heat is created, which is unfavorable in polymer formation, so this heat needs to be dissipated. The unreacted monomer is recycled, cooled, and compressed, and then pumped back into the system to regulate the temperature. And this ensures that the monomer can be polymerized to specifications. Once the polymer is made, it is removed from the reactor through dipping tubes, where the polymer goes through the polymer gas separation process. This starts with carrier gas, where steam and additive are infused with the polymer to deactivate the catalyst. The product is then filled into a discharge vessel, where unreacted monomer is recovered. When all the unreacted monomer is extracted, the polymer is then pumped out and goes into the purge vessel, where a single axis stir will mix nitrogen, which is pumped into the purge vessel. Nitrogen helps stabilize the polymer and removes any moisture and volatile materials. The nitrogen is also used to propel the powder to the powder silo, where it awaits its last leg, the extrusion and mixing process. This starts by feeding the plastic material along with water and additive through a hopper into a barrel of the extruder. The polymer powder is gradually melted by the mechanical energy generated by the turning of the screw. Excess water and off-gas is removed via vacuum port, and the molten polymer is forced into an underwater cutting die. This is to cool and shape the pellets. The pellets are then driven into a centrifugal dryer where water is separated from the pellets. The pellets are transferred to a series of mixing silos for storage purposes, while air is integrated into the mixing silos to recirculate the pellets to prevent clumping and to facilitate the packing of the final product. And this is how polymerization is done in a gas phase reactor. Thank you so much for watching. Please like and subscribe.
Okay, so that was about the polymerization reaction. And Bhargav, I told you already the result is being postponed because one of the exams have not been conducted for your juniors. So they will release it together, I believe. So we have seen catalytic alkylation, catalytic isomerization, and catalytic polymerization. Now I'll show you the extra notes which I have shared on your e-content also. Okay, so in your e-content, if you see, there are two PDFs uploaded for catalytic reforming. One will be the PPT and the other one will be the book pages. And so these are the book pages. Yes, Shyam, I'll inform. Okay. Okay, those steps are given here. Naphtha hydro treatment आपको यहाँ से देखना होगा. The one which we have in the PPT, it is naphtha cracking. So naphtha hydro treatment and naphtha cracking दोनों में difference है. तो naphtha hydro treatment के लिए आपको यही से आंसर लिखना पड़ेगा. No, Bhargav, no update about that also. आपको जो एकेडमिक शेड्यूल आया था वही है हमारे पास, उसके अलावा हमारे पास कोई अपडेटेड शेड्यूल नहीं है. ओके, देन कैटलिस्ट रीजनरेशन हम कैसे करेंगे, व्हाट इज ऑब्जेक्टिव, ये सब हमने देखा था. कैटलिटिक पॉइजन्स ये सब हमने देखा था. अभी हमें और क्या बाकी है यहाँ पे. दैट्स इट अप टू कैटलिस्ट पॉइजन्स. ओके, इसमें स्पेस वेलोसिटी एक नया टर्म है जो आपने उसमें नहीं देखा होगा. देन व्हाट इज मोनोमेटालिक, बाइमेटालिक एंड what is the active site for catalytic reforming, ये सब यहाँ पे होगा. So whichever question will be asked, अभी मैं आपको जो question शेयर करूँगी चैप्टर 4 का, जब उसमें से आंसर ढूंढोगे तो आपको ये वाला पीडीएफ भी रेफर करना पड़ेगा आंसर्स के लिए. अगर यहाँ पे भी नहीं मिल रहा है देन यू विल लेट मी नो सो दैट आई विल गिव यू द आंसर्स. So as of now, chapter 4 is over. We will be moving to chapter 5 and then we have chapter 6. Chapter 5 and 6 is purely on petrochemicals, जिसमें हम C1, C2, C3, C4 petrochemicals के बारे में देखेंगे कि पेट्रोकेमिकल्स प्रोड्यूस कैसे होता है. जैसे आप ज़ाइलिन है, टोलुवीन है, विनाइल क्लोराइड है, पॉलीविनाइल क्लोराइड है, फिर योर नैफ्थलीन्स है, ये सब कैसे प्रोड्यूस हो रहे हैं हम देखेंगे इन चैप्टर 5. कौन से कॉम्पोनेंट्स हम देखने वाले, आई जस्ट शो इट टू यू नाउ. So this is your syllabus. तो पॉलीमराइजेशन, अल्काइलेशन, आइसोमराइजेशन एंड रिफॉर्मिंग प्रोसेस चैप्टर 4 में था, वो हमने कंप्लीट कर दिया है. अभी जो है ये इंट्रोडक्शन टू पेट्रोकेमिकल्स. So petrochemical classification, we have first generation, second generation and third generation petrochemicals. First generation में C1, C2, C3, C4 and BTX है. Then you have second generation petrochemicals like syngas, ethylene oxide, formaldehyde, chloromethane, vinyl chloride, ये सब second generation में आएगा. And जो third generation petrochemicals है जैसे olefinic polymers, plastics, rubbers, polyethylene, polypropylene, polybutadiene, SBR, ये सब हम यहाँ पे देखेंगे. ओके, तो ये पेट्रोकेमिकल्स का जो चैप्टर है, दिस इज व्हाट एक्चुअली इज हैपनिंग इन द इंडस्ट्रीज. रिफाइनिंग कम जगह पे होता होगा बट ऑल ओवर द ग्लोब पेट्रोकेमिकल्स का इस्तेमाल होता है. रिफाइनरीज कम जगह पे होंगे बट ये जो पेट्रोकेमिकल प्रोडक्शन है, रिफाइनरी के अलावा काफ़ी अलग यूनिक प्लांट्स है जो रिफाइनरी के बाद ये पेट्रोकेमिकल्स को प्रोड्यूस करती है. वहाँ से रिफाइनरी से वो ले लेंगे फीड स्टॉक और वो पेट्रोकेमिकल प्रोडक्शन में काम करते हैं. So this is on petrochemicals. We will be talking about it when we meet in the next class tomorrow. Okay. So I'll try to put the questions for chapter 4 by today, else I'll put it tomorrow. फिर आप chapter 4 के answers ढूंढने लगो and then you let me know. Okay. Any doubts so far? आज है last date भार्गव, today. The submission of the assignment, you had to do it by today, so you still have time till the evening. You can write and send it to me. Mail कर देना मुझे. Yes, no problem. Okay, so only 25 of the participants are here. So drop your number in the chat box and you can exit the meeting if you have no doubts. 15th की बात हो रही थी, but no, not, I'm not sure, Shyam. Those who don't have any doubts, please drop your number in the chat box and you can exit the meeting.